Hello, I am Kat, and today I'll be presenting our recent paper on beach recovery. This paper focuses on the Southwest, and it was based exclusively on freely available data collected as part of the Southwest Coastal Monitoring Programme. We focus on beach recovery following the 2013-14 winter because storm conditions during that winter were unprecedented across the entire Western European seaboard. What made that winter so unique wasn't simply the unusually large wave heights or the fact that storms during that season lasted double as long as those of the second most energetic winter. Most importantly, perhaps, the total number of storm days during that winter was 200% greater than the second ranking season. As a result, most of the Atlantic European coastline was left at its most eroded state in decades. Scientifically, though, the events of that winter offered a unique opportunity to study storm response on a wide scale, and indeed the research that followed greatly increased our understanding of how the coastline responds to storms. One of the studies done in the wake of that winter focused on 157 beaches around the southwest and seek to identify the morphological and forcing parameters that control their response. They classified beaches in 4 broad groups or classes based on 2 response parameters: the magnitude of the overall observed beach volume changes and the longshore and crossshore variability in the observed changes. And they found that each group was characterized by specific parameters such as beach length, degree of exposure, and orientation relative to the prevailing storm direction. For example, open beaches exposed to near shore normal high energy waves experience the largest spatially uniform sediment changes, whereas more sheltered sites exposed to oblique angles of wave approach showed a rotational response with limited net changes. So their findings imply that if we know the type certain beach is, we can predict the type of response it will have for a given storm. Now, however, to understand how our beaches change over time, we need to know as much about how they recover from storms as about how they respond to them. And our study aimed to enhance the understanding of post-storm recovery characteristics. Now, we looked at the recovery of 23 sites included in the previous study to investigate the following questions. So firstly, to what extent have those beaches recovered? Have they returned to their pre-storm states? And did the spatial patterns or the general characteristics of the recovery, were they similar to those of storm response? And did beaches within the same group recover to the same extent and exhibit the same spatial patterns? Secondly, we wanted to look at the temporal pattern of recovery. So how did sediment return to the beaches? Did it return over the first season, or did this happen gradually over 1 or 2 seasons that followed? And what was the role of wave forcing in the recovery for each group? So to answer our first question, we used a combination of either airborne LiDAR or on-the-ground RTK GPS continuous survey data, depending on the availability, collected in 2012, 2014, and 2017. And we created digital elevation models of beach surfaces for each epoch. Then by subtracting 2 DMs, we get a DM of difference, or DOD, that corresponds to the elevation difference that occurred between the 2 epochs. So, for example, the difference between the post-storm and latest DMs would correspond to changes occurring over the recovery period. To answer our second question, we used biannual survey data collected across beach transects, and we either summed up the profile beach volumes across the entire beach to give us a measure of beach volume at each time step, or where rotation was observed, we separated the beach in longshore sections and added the profile volumes for each section separately at each time step. Now, when looking at the DODs for all of our sites, we found that for most sites exhibited a markedly similar patterns of sediment changes over the response and recovery periods, only in reverse. So accretion seemed to have occurred over the areas that had originally eroded in response to the 2013-14 winter storms. Watergate's Bay, shown here, presents a characteristic example of this behavior. This is a class 1 site, so it's exposed to high energy near shore normal wave approach, and it typically experienced large uniform changes during both phases. And as you can see, the spatial patterns of erosion and accretion during the two phases are very closely matched. Another example is Pantewan Sands. This is a class 3 site, so it's sheltered and embayed. And this site had a typical behavior of this group, exhibiting a spatially variable response to the 2013-14 winter storms, with negligible net changes and similarly characteristics of it during the recovery period. So both a spatially variable recovery with very small negligible net changes. So across the 23 sites, the magnitude of changes observed over the response and recovery periods were fairly consistent within groups and were strongly correlated. Class 1 sites, so these would be the open high energy sites, lost the largest volumes of sediment over the response phase, but also recovered the largest volumes of sediment over the recovery period. Class 2 sites, which were similar in terms of their morphology, but exposed to slightly less energetic wave climates, showed more moderate changes during both phases, but also spatially uniform. Class 3 sites, like the sheltered embayed sites, had a generally variable behavior, but tended to exhibit limited net changes with large sediment redistribution over the entire beach. While class 4 sites showed a rotational behavior with very small net changes but large longshore sediment redistribution in opposite directions during the two phases. In terms of overall recovery achieved, our results showed that on average over the 3-year recovery period, beaches belonging to the first group had recovered roughly 3/4 of the sediment they'd lost, while those in the second group had returned to the pre-storm levels, with some overcompensating even their lost sediment. Now, recovery for the third group was variable, but in general there were very limited changes in both phases. And finally, for sites that showed a rotational behavior in response to the 13-14 winter storms, recovery constituted in rotation in the opposite direction. So even though there were some exceptions, recovery was generally coherent within the beach classes. And this suggested that we could then investigate the progression of recovery by focusing on one site from each group. So for this purpose, we looked at Perranporth, shown here in yellow, Fistral, shown in red, and Porthmeor, shown in green on the north coast of the southwest, to represent classes 1, 2, and 3 respectively, and Carlisle Bay, shown in blue on the south coast, to represent class 4 sites. Now, the 3 sites on the north coast are exposed to an energetic wave climate with a dominant direction slightly north of west, while Carlisle Bay is exposed to a less energetic bidirectional wave climate with 2 dominant storm directions, a primary, which is southwesterly direction, and a secondary easterly direction. So when we looked at the beach volume data derived from the biannual profile survey dataset for our class 1 and class 2 sites, we saw that even though the timing of the surveys was not always consistent, a seasonal signal is clearly evident, with erosion occurring over the winter months and accretion occurring over the summer months. Now, analysis of the post-storm autumn beach volumes, shown here to the right, reveals an annual increase in beach volumes at the two sites, but with very different relative magnitudes. So while Fistral, shown at the bottom row, overcompensated its lost sediment after the second summer, Perranporth, shown here at the top, though continuously regaining sediment, had not fully recovered by autumn 2018. Now, in contrast, the Class 3 sites showed a very weak seasonal signal and actually accreted during the 2013-14 winter, but it also showed much smaller net sediment changes throughout. A comparison of the beach volume in relation to relative wave power indicated that for Class 1 and 2 sites, beach volumes were strongly correlated with wave power, with lower than average wave power associated with higher beach volumes, while higher than average wave power associated with lower beach volumes. Conversely, at Porthmeor, the Class 3 site, there was very little correlation between volumetric change at the beach and relative seasonal wave power. So it seems that wave power was the primary control of beach volume changes at Class 1 and 2 sites, but not for the Class 3 sites. Now, Carline Bay is a typical Class 4 site on the south coast, which showed very little, very small overall net changes, and it also did not display a strong seasonal signal despite the evident seasonality in the cumulative wave power. And that indicates that wave power alone was not the primary control of beach volume changes at this site. But what we can see, looking at the volume changes at the two ends of the beach, is that they exhibit a synchronous out-of-phase response, suggesting that sediment was being transported from one end of the beach to the other and back again, and that resulted in a rotational behavior, which is typical of this group of beaches. And we can also see that the 2013-14 winter storms resulted in significant change in planform, although the overall net change, the overall net volume changes were very small. Now, in this case, recovery constituted in sediment being driven in the opposite direction, which once again happened gradually over the next few years, so that the beach returned close to its pre-storm planform by the end of 2018. Now, this synchronous out-of-phase behavior is also mirrored in the correlation between the normalized beach volumes at the two ends of the beach, of course indicating this rotational behavior. Now, to see how rotation related to wave direction, and drawing from previous studies, we used two parameters: the rotational index to express the direction of beach rotation, so clockwise and anti-clockwise, and the wave directional power index to describe changes in the directional power balance between the two primary directions relative to the long-term average. So as with previous studies, what we found was that these two parameters were also closely correlated. So higher than average contributions of the primary direction were associated with a clockwise rotation, whereas lower contributions were associated with an anti-clockwise rotation. So in this case, it is the balance between the dominant wave directions that seems to be the key control over changes in beach planform. So to summarize, what we found was that beaches responded to and recovered from storms in a coherent manner, and that the magnitudes and spatial patterns of post-storm recovery can, for the most part, be grouped into four main coherent classes. And this in turn suggests that the existing classification developed to describe storm response may also apply to overall beach behavior, including recovery. We found that those sites that lost most sediment during the 2013-14 winter storms also subsequently gained the most sediment over the recovery period, though they did not necessarily fully recover. Fully exposed sites displayed the highest gross volume changes of both eroded and recovered sediment, but recovered at the slowest rate. And this means that they remained in a more vulnerable state over multiple winter seasons. Recovery for sites exposed to a bidirectional wave climate is driven by a switch in the directional power balance between the two dominant directions. So potential future changes in this balance will affect the planform of these sites. Now, we feel that the observed coherency within each of the 4 study groups suggests that regional monitoring programs could make considerable savings by strategically targeting monitoring at a limited number of representative sites within each class, rather than monitoring all sites within a region. This approach may also open the opportunity for higher temporal resolution monitoring on fewer sites that will in turn enable the study of smaller temporal scale processes. And with this, I thank you for listening, and I am happy to take any questions you may have.